Here is a question on general organic chemistry. Read the question carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Resonance stabilization requires that the lone pair or charge can delocalize into an adjacent pi system, such as AC is equal to O group, through orbital overlap. For this overlap to occur, the orbitals must be able to achieve the necessary geometry, ideally parallel p orbitals. Moving on to the next step. In cyclohexanone with a negative charge, carbanion, at the alpha carbon, the carbanion lone pair is adjacent to the C is equal to O group. The p orbital on the alpha carbon can overlap with the pi system of the carbonyl, giving resonance stabilization as an enolate. This is well-known resonance stabilization. Moving on to the next step. The oxabicyclic compound has an oxygen with lone pairs adjacent to the carbonyl. The lone pairs on oxygen can delocalize into the C is equal to O, providing resonance stabilization, similar to an ester or lactone type resonance. And for the final step, the bicyclic system with a negative charge at the bridgehead adjacent to a double bond allows the carbanion to delocalize into the pi bond, providing resonance stabilization, allylic type anion stabilization. This is the critical case. In the norbornane bicyclo 2.2.1 skeleton, the carbanion is located at the bridgehead carbon. Brett's rule states that a bridgehead carbon in a small bicyclic system cannot bear a double bond or effectively participate in pi overlap because the geometry forces the bridgehead p orbital to be perpendicular to the carbonyl pi system rather than parallel. The rigid bicyclic framework prevents the necessary orbital alignment for resonance delocalization between the bridgehead carbanion and the adjacent carbonyl group. Therefore, the carbanion at the bridgehead of norbornane adjacent to a ketone cannot be resonance stabilized. The p orbital at the bridgehead is orthogonal to the C is equal to O pi bond due to the rigid cage geometry, a violation of Brett's rule situation. Why other options fail? Options A, B, and D all have geometries that allow proper orbital overlap for resonance delocalization. Option C is unique because the bicyclo 2.2.1 bridgehead geometry prevents the required orbital alignment. Therefore, the correct answer is C. Therefore, the correct answer is option C.